Welcome to the pathology department. Today, we're diving into the world of microscopy, the absolute foundation of what we do here. First things first, if you'll need your own microscope. But before you spend all day looking at slides, let's make sure you're set up correctly to avoid some painful mistakes.
Okay, got it. So, I need to learn how to use this thing properly. It looks complicated.
This is it right here. Now look closely at this diagram. You see the eyepiece, the stage where the slide sits and the condenser below it. But there's more to it than just pointing and clicking. Many residents end up with back pain or wrist strain because they didn't set up their workspace correctly from the start.
Musculoskeletal complaints. Wait, is that like hurting myself using a microscope?
Exactly. We're talking about ergonomics. Your setup matters just as much as knowing how to focus. Poor posture, awkward angles, or forcing yourself into uncomfortable positions can lead to chronic pain. Think of it like typing on a computer. Like, if you don't set it up right, you'll regret it later.
So, before I even look at a single slide, I need to worry about my own body. That makes sense. So what are the basic principles?
Great question. First, adjust the chair height so your feet are flat on the floor and knees are slightly higher than your hips. Position the microscope so you're looking slightly down, not leaning forward. Keep your arms close to your body and use the controls with your dominant hand if possible.
Okay, so like working at a proper desk. What about the microscope itself?
Good. The microscope should be positioned so you don't have to twist your neck to see. Most importantly, don't force the focus knobs. If something doesn't feel right, stop. Take breaks every hour, and remember, consistency is key. Start with short sessions and build up your time gradually.
This seems almost too simple. Is it really that important?
Incredibly important. A poorly set up workspace makes everything else harder. Reading slides, taking notes, collaborating. And taking these steps now will save you from discomfort and make your path through pathology much smoother.
Got it. So no more microscope posture disasters. Thanks, Professor. I feel like I can actually start learning properly now.
Exactly. Now let's move on to the mechanics of focusing, how to actually see those microscopic wonders. Uh, all right, class, let's talk about microscope posture. First things first, you want a neutral neck position.
Okay, so what does that even mean? Neutral neck.
Good question. It means you shouldn't be straining your neck or using any extra muscle tension just to look through the eyepieces. Your eyes should be aimed straight ahead or maybe slightly down, not up or down. at an extreme angle.
Wait, why is that important? I mean, I can probably look through the eyepieces, even if my neck is weird.
Exactly. That's where bad positions come in. Flexing your neck, like dropping your chin to your chest or jutting it forward, um, can cause muscle fatigue and actually affect the precision of your observations. Turning your head side to side is another no-no.
So, what's the best way to achieve that neutral position?
Tilt head microscopes are designed for this, but even with a standard setup, you can just adjust the tilt using a three-ring binder under the microscope. The key is to get your eyepieces no more than 30 degrees from the desk surface.
Got it. So it's about finding that sweet spot where my neck isn't working too hard. Got it.
Now, let's talk about posture. I know it sounds simple, but keeping a straight back is crucial. Nothing ruins concentration like slouching.
So just like the neck, my whole body needs to be in a neutral position.
Um, and unlike the neck, this one requires some help. You'll need a chair with a supportive back to maintain that straight posture um, for the duration of your session.
Okay, so the key takeaways are neutral neck, straight back, and using a good chair. Got it. Got it. Thanks, Professor.
All right, class. Let's talk about proper sitting posture for our microscope work. The key is to have your chair positioned so your head and neck rest comfortably on your spine.
Wait, why is that important? I've been sitting like this for a while without issues.
Good question. Um, Poor posture can lead to chronic neck and back pain. And to achieve this comfort, you have two options. Adjust your chair back to a more vertical position.
Or add to support.
So, you mean the chair shouldn't be tilted forward like mine is?
Exactly. And here's another crucial point. Always sit directly in front of your microscope. Having it off to the side might seem practical for desk space, but it quickly leads to back and neck pain.
I see. So even if I need more workspace, I shouldn't sacrifice my posture. Got it. What about my arms?
Um, your elbows need, you'd be using both hands constantly, one for driving the slide, one for focusing. Both tasks can be done with either hand, but your elbows should rest on your desk for comfort.
So to summarize, proper chair height angle, no leaning forward, sit directly in front of the microscope, and supported elbows. That should keep me comfortable during long lab sessions.
All right, class, let's talk about ergonomics. One common issue people face is compression neuropathy in their arms while working at a desk.
Wait, why is that important? I mean, I sit at a desk all day, but I didn't know it was a thing.
It's more common than you think. Specifically, the ulnar nerve is often compressed when the elbow bends too much against a hard surface like a desk edge.
So you're saying that if I lean my arm on the desk all day, I could damage the nerve in my elbow?
Exactly. And that's why a padding is crucial. The point of contact between your arm and the desk needs cushioning to prevent that kind of nerve compression.
Okay.
Got it.
So what are some practical ways to do this?
There are several options. You could use pieces of rug or bath mats, sponges, mouse pads, or even commercial gel pads designed specifically for desk users.
So you're basically saying to put something soft under my arm whenever it touches the desk edge?
Yes, that's the idea. It's a simple fix that can prevent discomfort and potential long-term issues. Try implementing that in your workspace. All right, class, let's talk about the physical structure of a compound like Microscope. Even though there's variation between models, certain key components are pretty standard. Um, think of these as the building blocks.
Okay, got it. So it's not like every microscope looks exactly the same.
Exactly. Think of it like different cars. They all have an engine, wheels, etc. But the exact placement and controls can vary. But the essential parts for light microscopy are usually present.
Like what? What are we talking about?
Let's start with the light source. Most microscopes have a bulb, usually at the back. This light needs to go up, so it's directed by a mirror hidden within the base of the microscope.
Okay. So the light comes from the bottom and goes up through the stage. Wait, is that right?
Close enough. Now, to control the light precisely, there's the field diaphragm. It's usually located near the base, and its width is controlled with a knurled ring. Notice anything special about this diaphragm?
You mentioned it's a glass neutral density filter. Is that part of the diaphragm itself?
Exactly. The actual diaphragm controls the width of the light beam, while the optional glass filter sits on top of this diaphragm to adjust the light's intensity without changing its beam width. It's removable.
So adjusting the knurled ring makes the light circle narrower or wider. What does that even do?
Great question. Closing the diaphragm, making the circle narrower, reduces the amount of light hitting the specimen. This can be useful for increasing contrast in certain situations. Think of it like adjusting the aperture on a camera.
Okay, narrowing the light circle reduces brightness and increases contrast. Makes sense. What's next?
Next are the screws to center the substage condenser. These are located on either side of the microscope, usually near the bottom, near the stage. They're crucial for ensuring the condenser is properly aligned.
So these screws are for alignment. What happens if they're not centered?
If the condenser isn't centered, the light beam won't be properly aligned with the optical axis. This can lead to uneven illumination and make focusing difficult. It's a critical step for getting sharp, cooler illumination.
Okay. So alignment is key. What comes after that?
The focus knobs, every microscope has these coarse and fine focus knobs. They're usually located near the bottom, near the stage, but sometimes near the eyepiece. The coarse knob makes large adjustments, while the fine knob makes the small, precise focus needed for high magnification.
All right, focus is covered. Last item?
Finally, the knob to raise and lower the condenser. This is vital for cool air illumination. By moving this condenser up and down, you adjust to the distance between the condenser and the specimen, focusing the light precisely onto the object being viewed.
Okay. So, putting it all together. Light source, field diaphragm, condenser centering screws, focus knobs, and the condenser height knob. Got it. So cooler illumination relies heavily on all these parts being properly adjusted.
Precisely. These are the mechanical workhorses of the microscope. Understanding their functions is fundamental before we even get into the objectives and eyepieces. So all right, class, let's get familiar with this microscope. First up, you'll notice a knob right near the base.
Okay? What's that knob for? Does it do something important?
Exactly. That knob flips the condenser out of the light path. And when it's flipped down, the light can pass through the specimen at the lowest power setting. It's crucial for initial viewing. And
Wait, why is that important? Well, doesn't the condenser just focus the light anyway?
Great question. Flipping it out removes excess light. That gives you a cleaner, less glare-filled image when you're just starting out. It's like turning down the brightness before you zoom in.
Okay, makes sense. So it's about controlling the light intensity before magnification.
Exactly. Now, looking through the eyepieces, you'll see a small ring labeled diopter.
Is that for adjusting the eyepiece? Like, if my eyes are stronger or weaker than yours?
Spot on. It's a diopter adjustment ring. It lets you, fine tune the eyepiece for your specific vision. It ensures the image is perfectly clear regardless of your visual acuity.
That's pretty neat. So it's personalizing the view for each person using the microscope.
Yes. Now, these are the objectives. You'll see different lenses right above the stage.
So these magnify the specimen. What's the difference between the ones I see?
These are the objective lenses. They're the real magnifying powerhouses. The different lenses you see have varying magnifications like 4x, 10x, 40x, etc. each gets progressively more powerful.
So the higher the number, the bigger the magnification. Got it.
Correct. Now, below the stage, you'll find the aperture diaphragm. It's that knurled ring.
Knurled ring? Like it's got ridges so it's easier to turn? What does it do exactly?
Yes, the knurling makes it easier to grip. And its purpose, it controls the size of the light cone hitting the specimen.
So adjusting this changes how much light hits the slide. How does that affect the image?
That's a fantastic question. Adjusting the aperture diaphragm changes the contrast and quality of the image. By narrowing the light cone, you increase contrast, making details pop. Wider openings let in more light, but can wash out finer details.
Okay. So it's like dimming the lights to get a sharper picture?
Exactly. Think of it as controlling the spotlight versus a floodlight on the specimen. Now, finally, the stage. Look underneath.
I see the stage clips. But the text mentioned the slide holder was removed. Why would someone do that?
Precisely, the slide holder or clips is removed here. This allows the slide to move freely on the stage. Many pathologists prefer this as it facilitates certain types of observations or slide manipulations.
So it's for specific techniques, not general use?
Often, yes. And it gives the user more freedom with the specimen placement. And remember, this whole setup is shown in figure 1.1, which I encourage you to look at now. I have 2021, and I can't come back here as therapy. But standard and general making in materials, we're discussing the parts of a microscope. I know the text mentioned it, but let's break it down visually.
Wow, that diagram is really detailed. So, Professor, looking at this, what's the most important part we should focus on first?
Great question. Let's start with the eyepiece or ocular lens. It's a circular part you look through. It magnifies the image created by the objective lens. Now, wait, why is that important? Because without proper magnification, those tiny tissue samples would be nearly impossible to analyze accurately.
Okay, so the eyepiece magnifies the image. But what about these other lenses right below it? Are those objective lenses?
Exactly. And there are several of them. The objective lens closest to the specimen provides the highest magnification. The lower magnification objectives are better for finding specific areas of interest within the sample. So you could say they are the workhorses of the microscope.
That makes sense. So the eyepiece adds more magnification, and the objectives provide the base magnification. But what about this platform the slide sits on? That looks like the stage.
Sharp observation. The stage holds the specimen slide securely in place. Many stages have mechanical controls that allow you to precisely move the slide horizontally and vertically. And this is crucial for examining kind of different sections of a tissue sample.
And this lever here, the coarse focus knob, is for making big adjustments to the focus, right? And the smaller knob is for finer adjustments.
So one case on the coarse focus knob is used for initial focusing, especially at high magnifications as it moves the stage up and down in larger increments. The fine focus knob makes precise adjustments for sharp, clear images. Using them effectively is key to getting a good look at the tissue architecture.
Okay, so we've got the optics and the mechanics. What about this part that looks like a little house? Is that the condenser?
The condenser is crucial for focusing the light beam onto the specimen. It sits below the stage and consists of lenses and apertures. The iris diaphragm part of the condenser controls the amount of light reaching the specimen. Adjusting it properly is vital for contrast and resolution.
Okay, so all these parts work together. The eyepiece and objectives magnify. The stage holds the sample. The focus knobs sharpen the image. And the condenser manages the light. Got it.
Excellent summary. Understanding the function of each part is fundamental to mastering the microscope, which is essential for accurately interpreting tissue samples in surgical pathology. Remember, precision with the instrument leads to better diagnostic outcomes. All right, class, let's talk about the mechanics of this microscope. First up, you'll find knobs that move the stage. Crucial for precise observation, they allow controlled movement along the X and Y axes when the slide holder is in place.
Okay, so these knobs move the slide left to right.
And front back.
Got it.
Exactly. Now let's talk about controlling the light. You won't see the mechanism itself, but there's a knob or sliding bar that adjusts the voltage to the light bulb, effectively controlling the brightness.
So that knob just controls how bright the light is. That makes sense.
Now, let's move into a slightly more complex area, but I promise it's fascinating. We're going to review some optics here. Helium illumination is a key concept, and while there are great resources for a deep dive, I'll give you the essence.
Okay. Sounds good. What's the essence?
The basic idea is about how light travels through the microscope. It starts from the light bulb at the back, is redirected upward by a mirror, and then is shaped by a diaphragm at the base. This shaped light is either focused down to a pinpoint or spread out into a wide cone, all thanks to the lenses and diaphragms involved.
Right. So the mirror flips the light path, and the diaphragm controls the shape of the light beam? That seems important.
Yes, you've got the core elements. The mirror redirects the light upward, away from its original path, and the field diaphragm acts like a gatekeeper, shaping the light before it reaches the specimen.
So you mean the field diaphragm controls how the light spreads out before it hits the slide?
Precisely. It's a crucial part of achieving even um, illumination across the field of view.
That covers the basic mechanics and the optical principles.
All right, let's talk about how we see things clearly, especially tiny things under a microscope. One key part is the diaphragm. Think of it like a spotlight on a stage.
Okay, like a spotlight? So it directs light.
Exactly. It sends a column of light upwards towards the slide. But that's just the start. This light column isn't uniform yet.
Okay, got the spotlight part. But what's the condenser you mentioned earlier?
The condenser is crucial. It takes that broad column of light from the diaphragm and squeezes it down into a tighter, more concentrated beam. This makes the light even and bright right where the specimen is.
So the condenser makes the light sharper and more focused for seeing the tiny details. Wait, why is concentrating the light important?
It's about illumination. Concentrating the light makes it brighter and more even on the specimen, giving you a clearer, sharper image. Think about it like shining a flashlight versus as a floodlight, the flashlight concentrated light gives you better detail on a small object. And
Got it. So concentration equals better visibility for the tiny details.
exactly one of the now let's talk about focusing itself. This is a fundamental principle. When light passes through a lens, like in your glasses or the microscope, the light rays bend. They converge, meaning they come together towards a specific point on the other side of the lens.
Converge? Like they're aiming for one spot? Okay, so the image gets sharp there.
Yes. That point where all the light rays meet is where the image is in sharp focus. In your own eye, ideally, this focusing point lands precisely on the retina, allowing you to see clearly.
Ah, so for the eye, sharp focus means the image point is right on the retina. But you mentioned if the eye is too long or too short, corrective lenses are needed. That sounds familiar.
Right? So that's just how lenses work in general. And now, back to the microscope. A modern microscope uses this focusing principle, but with many lenses and diaphragms in a row. But the core idea is the same. There are essentially two separate paths for light. One goes through the specimen stage and the objectives, focusing for high magnification. The other goes through the eyepiece, focusing for your eye. And the key is that both paths need to be focused properly. They need to converge to a sharp point at their respective levels within the microscope.
So it's like having two different focusing points built into the system. one for seeing the specimen clearly, and one for seeing that image through the eyepiece clearly.
You've got it. The microscope is designed so that light passing through the specimen and the objectives converges correctly for viewing through the eyepiece. And the eyepiece itself also focuses that final image for your eye. All right, let's talk about how microscopes create a sharp image. Ever wonder why you sometimes see the same pattern in different places inside the microscope?
Wait, what do you mean? I know you need to focus the lens, but how does the image appear in multiple places?
Imagine there's an invisible path for the light rays inside the microscope. Along this path, there are 4 key points where a perfectly focused image of your tissue appears. These are called the conjugate planes.
Okay, so there are 4 points. Let's hear them.
The 4 conjugate planes are the field diaphragm, the slide or specimen itself, the fixed diaphragm inside the eyepiece, and the point where your retina or camera would be.
So the image appears sharp at the field diaphragm, on the specimen in the eyepiece, and on my eye or camera.
Exactly. Now, here's the really important part. If you want a sharp image on your camera phone, you need to adjust the distance between the phone and the eyepiece. To get that focused image, you need to move the camera lens away from the eyepiece until it reaches roughly the position where your retina would be. That's because the camera sensor needs to be at one of these conjugate planes to capture a sharp image.
So it's like the image is physically projected along this path and different parts of the optical system just capture different slices of the same focused image.
You've got it. That's the fundamental principle here. It explains why we can see the image clearly through our eye and why cameras placed at the correct distance work so well with microscopes. All right, class, let's talk about cooler illumination. It's a technique used to align the lenses and diaphragms in a microscope to get the best possible image.
So is this like some secret setting in microscopes?
Not exactly a secret, but it's crucial. Achieving cooler illumination means aligning all the parts so that the light rays create a sharp, even image across the entire field of view.
Wait, why is this alignment so important? Can't you just focus and be done with it?
Good question. Without proper cooler illumination, the image quality suffers significantly. You might see uneven brightness, halos around bright points, or blurry areas. It's essential for both observation and photography.
Okay, so how do you actually do this? The textbook just says, align all these lenses and diaphragms.
Let's break it down. First, place a slide on the stage and then adjust the eyepieces so they're the right distance apart for your eyes. This ensures a comfortable viewing experience. Now focus on a slide using your 10x objective. This is the starting point for the alignment process. From here, you typically adjust the condenser height and the diaphragm to fine-tune the illumination.
So Just putting a slide on the stage and focusing with the 10x objective is part of it. But there's more steps involved.
Yes, the initial steps are straightforward, but the full alignment involves adjusting several components. The key takeaway is that cooler illumination is achievable, and while understanding the physics helps, you can learn the technique through practice.
Got it. So even if I don't know all the physics, I can still get a better image by doing this alignment right.
Exactly. So it's a practical skill that directly impacts the quality of your microscopic work. All right, Haas, let's talk about adjusting your microscope for comfortable viewing. First, if your microscope has just one adjustable eyepiece, you need to start by closing that part of the eyepiece.
Wait, why is that important? Can I just look through it normally?
Exactly. And by closing it, you're preparing the optical path for proper focusing. And then you'll use the regular focusing knob to get a clear image.
Okay, got it. What about microscopes with two adjustable eyepieces?
Great question. For those, either eye can be used first. It's all about finding the diopter adjustment that works best for your vision.
The diopter adjustment? Is that like reading glasses?
You got it. The scale on that ring shows diopters, and the positive direction is indeed like reading glasses. It helps compensate for individual vision differences.
So once one eye is focused, I just close that eye and adjust the other one.
Yes, that's correct. That's how you achieve comfortable binocular vision without eye strain.
Got it. What about the aperture diaphragm on the substage condenser?
Good. Before you start viewing, make sure your aperture diaphragm is completely open. Be sure to check which direction opens it on your specific microscope model.
Clockwise or counterclockwise? Is there a right way?
That depends entirely on your microscope model. Always consult your manual. And the reason for fully opening it, it ensures maximum light reaches your specimen for optimal viewing.
I see. So that aperture diaphragm controls the light coming through the condenser lens.
Exactly. It's crucial for proper cool illumination, which gives you even glare-free lighting across your field of view. All right, class, let's talk about how microscopes work. One thing you might not realize is that the optimal viewing distance or the circle of light varies depending on which objective lens you're using.
Wait, what do you mean by the circle of light?
Exactly. To find this specific circle for each objective, you'll need to remove the eyepiece and look down into the eye tube. You'll see a circle of light there.
Okay, got it. So how do I find this circle?
Great question. Once you see that circle of light, you need to adjust the aperture diaphragm on the condenser. Close it until only a quarter of the field around the edge is illuminated.
So that's how you find the circle of light for each objective.
Yes. And now let's talk about something called parfocality. This is an important concept for multi-headed microscopes.
Parfocality sounds like a fancy word. What does it mean?
Parfocality means that if you focus the image at 40x magnification, you should be able to switch to 4x magnification and still have a clear image.
So it's like the focus stays the same regardless of magnification?
Exactly. This is different from cooler illumination, which is about even lighting across the entire field. Parfocality specifically refers to maintaining focus.
And this is really important for microscopes with multiple observers.
In a multi-headed microscope, which everyone needs to see the same thing clearly at the same time. And that's why parfocality is crucial.
So it's not just about the image being clear, but everyone needs to be in sync.
Exactly. And this can only be achieved with a microscope that has 2 adjustable eyepieces.
Okay, so that's the key takeaway. Finding the circle of light for each objective and understanding parfocality.
Perfect summary. Just remember, parfocality is about maintaining focus across different magnifications, and it's essential for collaborative viewing. All right, let's talk about focus adjustment on the microscope. And when you're working at the 4 times magnification level, you'll need to readjust your eyepieces. And that's because the focus changes. And so, everyone needs to be on the same page.
Okay, so at 4 times, the eyepieces need readjusting. Why is that?
Good question. The main focus knob adjusts the stage while the eyepieces have their own fine focus controls. When you change magnification, the distance through which light travels changes, so you need to adjust your eyepieces to maintain focus. Now, once everyone has adjusted their eyepieces, you should be able to see both the screen and the individual slide elements in focus at each objective. This is called parfocal.
Parfocal. So it means everything stays in focus when you switch objectives.
Exactly. But sometimes one objective might not perfectly align. If that happens, check if it's securely screwed into the objective turn. It might just need a tighter fit. If it's still not perfect, don't worry too much. If everyone follows the procedure, you'll all be in sync. The main focus knob can always be used by the driver to make final adjustments for everyone.
Got it. So parfocal means everyone sees the same thing without adjusting the main focus, right? But if one objective is off, we can adjust together using the main knob. That makes sense. What about those transparent or translucent things you mentioned?
Yes. Some specimens don't take up the stain we use well. So when we look at them under the microscope, they might appear transparent or translucent. So that's just something to keep in mind when preparing and observing slides. Good examples are calcium oxalate and suture material, S to C cells, subsensors oxalate S to C with the so invisible. They can be essentially invisible during normal viewing, but will glow, under polarized light. And
Wait, so they're not visible under normal light, but become visible under polarized light?
exactly. But most resonant microscopes don't have polarizers.
Oh, so what's a quick substitute?
Flipping the condenser out of the light path, just like you do when viewing it 2 times. This will cause refractile material to pop out and be easily visible.
So you mean flipping the condenser changes how light focuses?
The knowledge of different paths of light being focused at different planes can be useful. For example, if you are looking at a slide and see debris or dust in sharp focus, that debris must be located in one of the same planes in which the image path is focused.
So the focus tells you where the debris is.
All right, let's talk about microscopes. One crucial part is the diaphragm. It's located at the bottom of the eyepiece inside the tube, and it's actually quite protected from dirt.
Wait, so it's not usually exposed to dirt? That makes sense. Where exactly is it located again?
Yes, it's integrated into the eyepiece assembly. Now, this diaphragm serves an important purpose. It's the place where you can mount macular micrometer.
An ocular micrometer? What's that for?
It's a tiny ruler built right into the eyepiece. When you superimpose it on your image, it allows you to make very precise measurements of the specimen.
Okay. Got it. Now, what about debris? The text says if debris is out of focus. When the image is focused, it's probably on the condenser or the top of the eyepiece.
Exactly. Think about the focus plane. If the main image is sharp, but the debris isn't, that means the debris is likely on a different focal plane. The condenser and the eyepiece are much closer to the specimen than the objective lens.
So, the debris is either very close to the slide or much farther away than the objective lens can reach. Got it. And finally, the slide can be placed directly on the field diaphragm at the base of the microscope.
Correct. And the field diaphragm at the base isn't just for show. And I don't love this. Something it's a practical feature, especially during multi-head microscope sessions. You can place the slide directly on it, allowing everyone to share the same low power view, even lower than a 2 times objective.
That's really handy for group work. So, to quickly summarize, the eyepiece diaphragm holds the ocular micrometer. Debris focus indicates location, and the base diaphragm holds the slide for group viewing.
Perfect summary. Understanding these diaphragm locations is key to proper microscope operation and troubleshooting. All right, class, let's talk about the focal plane in microscopy. It's crucial to understand how it aligns with your slide on the stage.
So you're saying the focal plane is synchronized with the slide. Why is that important?
Exactly. Because when you're looking through the eyepiece or capturing an image, you'll get a reasonably focused image of the entire slide, not just a small portion. This trick works especially well with Kodachrome slides.
Kodachrome slides, I thought those were pretty much obsolete. So this applies to them too?
Yes. And if you're having trouble getting sharp focus at high magnification, it's likely one of two issues. Either the slide is upside down, meaning the cover slip is on the bottom, or the objective lens itself is dirty. All right, class, let's talk about microscope eyepieces. One of their key functions is correcting mild to moderate vision problems.
Wait, what? How does that work?
They're designed that way because the eyepiece itself can compensate for common vision issues. And here's the cool part. They're easier on your eyes because there's no additional lens in the way.
So you mean like reading glasses or for microscopes?
Exactly. But this only works for less severe cases or astigmatism. And, you know, for stronger vision problems, we need corrective lenses.
Okay, so what's the solution for people who wear glasses? Place
There are special eyepieces called high eye point eyepieces. They're designed specifically for people who wear glasses.
Why would someone need a higher eyepiece?
Because when you're wearing glasses, your eye is farther from the eyepiece. And if you weren't, these eyepieces account for that distance.
And they're labeled with an H or a spectacles icon, right?
Yes, that's correct. And interestingly, these specialized eyepieces can also benefit people who don't wear glasses, offering a slightly wider field of view.
So they're kind of like universal eyepieces?
Not quite, but they do offer more versatility. The key takeaway is that eyepieces can be customized to suit different vision needs and preferences. All right, let's talk about the mechanical stage. It's basically the set of brackets that secure your slide onto the stage, but they're more than just clamps. They allow you to move the slide precisely, left, right, and front, back.
So it's like a little slide holder with movable parts. What's the big deal about moving the slide?
The key is controlled movement, then, you know, getting better up and see the time like this. The problem of progress is, right, imaging, it's predictive for you need to systematically scan the entire slide. The mechanical stage ensures you move in straight parallel lines, so you don't accidentally drift off course and miss parts of your specimen.
Wait, why is that important? Why not just move the slide with your hands?
That's a good question. Moving it by hand can be tricky. You have to judge the distance carefully to avoid overlapping your scans or creating gaps. The mechanical stage provides that precision. You set the distance and it moves exactly that amount each time. crucial for ensuring you cover the whole slide systematically.
Okay. So it's useful for making sure you don't miss anything. Like a checklist for the slide.
Exactly, especially in cytology, where you're looking for subtle changes or abnormalities. Missing a small cluster of cells could be significant. The mechanical stage helps guarantee complete coverage.
But the text also says most pathologists don't like using them. Why is that?
Good point. With practice, pathologists develop a keen sense of muscle memory. They learn exactly how much to push or pull the slide with their hands to move just the right amount to get from one edge of the tissue to the next. They find the mechanical stage brackets themselves can get in the way or slow them down for routine work.
So, it's like learning a new skill. Mastering the manual movement becomes faster and more reliable than using the stage mechanism.
You could say that. Practice makes perfect, and for many, the speed and feel of manual movement become preferred for everyday examination. The mechanical stage is a tool that helps build that precision initially, but once you've got it down, you might find the brackets unnecessary.
Got it. So, the mechanical stage is like a crutch, helpful for learning or ensuring precision, but not always needed for experienced users.
A fair way to put it. It highlights the difference between absolute precision and efficient workflow. The mechanical stage enables the absolute precision needed for systematic scanning, while manual dexterity allows for efficient workflow for experienced users.
Okay, so the mechanical stage guides the slide movement, ensuring straight lines, while muscle memory allows experienced users to navigate quickly without the brackets.
You've got it. It's a feature designed to help with specific tasks, but its utility depends on the user's skill and the task's requirements. All right, class, let's talk about microscope stages. You've probably seen microscopes with movable parts, but did you know many still allow you to move the entire stage along the y-axis using those knobs?
Wait, why is that important? What does moving the stage on the y-axis even do?
Great question. It allows you to make parallel vertical sweeps across your slide at high power, even without using slide brackets. This can be really useful for scanning large areas of your specimen efficiently.
Okay, got it. So you're saying you can move the slide smoothly up and down in a straight line?
Exactly. But here's the tricky part. Because of the way the microscope inverts the image, learning to move the slide smoothly without jerky movements takes practice. It can take several months to perfect this skill.
Oh, I see. So the inverted image makes it harder to judge the actual movement. That must be frustrating for beginners.
It can be. Many students get discouraged initially, but don't give up on this skill. Mastering it is crucial for precise observation, especially at higher magnifications.
Okay, got it. So practice, practice, practice. Got it. Now, what about the rest of the text?
Yes. Some of you might be familiar with motion sickness. There are people who are very sensitive to vestibular ocular mismatches.
Vestibular ocular mismatches. Is that related to the microscope again?
Not directly, but let's see. When you look through a microscope, you're seeing a moving image that fills most of your field of view while your body is perfectly still. This mismatch between what your eyes see and what your body feels can sometimes trigger a reaction similar to motion sickness, like car sickness.
Oh, I get it. So, some people might feel sick looking through the microscope for a long time. Is that why some labs have mechanical stages?
Exactly. For those individuals who are sensitive to this, a mechanical stage can help by moving the slides smoothly, reducing the vestibular ocular mismatch. But for those of you not affected, it's just another tool to consider.
Okay, so just to recap. Moving the stage manually is a skill that takes time to master because of the inverted image, and some people might feel queasy from the moving image while their body stays still. Got it.
Perfect summary. Remember to focus on that smooth movement skill and be mindful of the potential for motion sickness if it affects you. You've probably noticed that on a moving slide, you can get that queasy feeling, right? It's kind of like being a passenger in a car, totally fine if someone else is driving, but rough when you're the one controlling the movement.
Wait, why is that important? Are we comparing slide microscopy to driving?
Exactly. As a resident, you spend a lot of time observing while the attending physician controls the slide. Some drivers are smoother than others, and a constant motion, especially to jerky movements versus smooth, continuous shifts, can really bother your stomach.
Okay, so the way they move the slide matters? What's the difference between constantly moving it and quick movements with pauses?
The constant movement throws your vestibular system, your balance system, into a tailspin. Now it's like having perpetual motion sickness. The quick pauses actually give your brain a chance to adjust.
Got it. So, what's the solution? You mentioned getting your sea legs.
First, don't worry. Most people bounce back within a few weeks. Your body adapts pretty quickly. And if the nausea is really kicking you in the teeth, there are medications that can help. All right, class, settle down. Today, we're diving into chapter 1, titled Using the Microscope. But before we get too deep into the technical aspects, let's talk about the practical side of being a pathologist.
Using a microscope? That makes sense. But isn't that what we usually focus on? What's the big deal about using it in a clinical setting?
Great question. The microscope isn't just for the lab. It's a tool you'll use constantly in clinical settings, studying your paperwork, looking up patient history on the computer, answering a page, or even going to retrieve an old biopsy sample. All these things can give you those crucial moments to catch your breath.
Wait, so you're saying that even during these brief moments, you're still thinking about the patient and the work at hand? That sounds stressful.
In desperate times, and let's be honest, medicine is often like that. You just do what you can. These small breaks are part of the job, and they help you stay focused and resilient.
So, you're saying that even amidst the chaos, it's important to stay organized and keep your head in the game?
You've got it. And these moments, whether it's reviewing paperwork or grabbing a biopsy sample, are opportunities to stay grounded. They remind you why you're doing this, to help patients and make a difference.
I see. So it's not just about the microscope. It's about maintaining your focus, even in tough situations. That makes sense.
It would, exactly. Now let's move on to how we actually use the microscope. But before that, let me know if you have any other questions about balancing clinical work with lab procedures.
Just one thing. You mentioned desperate times. Can you give an example of what that might look like in a real scenario?
Sure. Imagine you're getting in the middle of a busy shift and you've got multiple urgent cases. A momentary break might be as simple as quickly reviewing a patient's chart between procedures. It keeps you sharp and helps prevent burnout.
Okay, that really helps. So, it's about staying present, even when things get hectic.
You're grasping it perfectly. Now, let's dive into the mechanics of using the microscope. But before we do that, let me know if you're clear on how these breaks fit into the bigger picture.
Yes, I think I'm good. Thanks for breaking it down.
Anytime. All right, class, let's move on to chapter 1, using the microscope.